Okay, so here's my whiteboard. So what are some of the intermolecular forces that we've talked about?
Ion dipole, I think.
Okay, so we have ion dipole. Okay.
Dipole.
Dipole.
Hydrogen ionic interaction.
Hydrogen what?
Bonds.
And we included ionic interactions or ion-ion because it's actually attractive forces, but it's stronger. It's much stronger than intermolecular forces. Does that make sense?
Okay.
So even though we include it, it's not truly because its strength is so much greater than what you see in the case of all of the other ones.
Okay.
Okay. So what was the other one?
Those induction ones.
What do you mean? Oh, so induce. Which one induce?
Ion and dipole.
Ion induced. Induced dipole. And then dipole induced dipole. And then the last one.
Dispersion.
Dispersion.
Right?
Dispersion. Okay. I'm sure I said this, but I just want to be sure that I say it one more time. So these are all of the different interactions that we occur. Let's see. Anybody? Okay, let's see. But the dispersion actually is found in polar and in nonpolar molecules. So we get that happening regardless. So that's just kind of like a guarantee, right? But we know that that's also the weakest of all of them, right? You guys remember that? Yes, no, maybe?
Yeah.
Okay, good. So good job. Let's see. Board. Slides. Come on. Okay. Okay, so now you're familiar with all of them. You're familiar with how they work. We've talked about dispersionary forces in terms of them being induced, right? So those are the ones that we're going to see pretty much in everything, polar and non-polar substances. So that is a guarantee. So we know that molecules could have combinations of different forces. So we know that polar forces could have a combination of dipole interactions, and we can also have dispersionary forces in there as well too. Now, we also know that these forces, the IMFs, are going to also affect how things behave. They're going to affect our melting points. They're going to affect our boiling points. So depending on the forces that are involved, that's going to have a major effect in terms of how things are going to melt and boil. Okay. And if we kind of think about when we had our water, you guys remember the water experiment? What were some of the data results that you guys got when you compared the Epsom salt to salt? Were they the same values Were they different values?
If I remember correctly, they were different.
Okay. And how were they different? Do you guys recall?
Was that with the one that we had to boil the salt?
That is correct.
So it was different because some of them would boil faster.
Okay. So what do you mean by boil faster?
Like,
So speed-wise, they would boil faster?
yeah, but like
Okay.
the time.
Okay, what about the temperature? More importantly, the temperature.
The temperature definitely would change.
Okay, so did your boiling points change on those? Let's say 5 grams of Epsom salt compared to 5 grams of sodium chloride of salt. How did they compare to each other?
Let me get my notes.
One was a lot higher. The boiling point was a lot higher for one.
The boiling point was a lot higher for one. Which one was it more higher for?
I think
Or-
it was the Epsom salt.
It was the Epsom salt?
I think so.
Yeah, so in theory, that's what should have happened, right? Because if we think about it, what's happening in the case of the Epsom salt? So Epsom salt is what? What is the chemical formula for Epsom salt?
Magnesium something.
Magnesium sulfate. Okay. So what happens to salts when they go into solution, into water?
They
It-
disperse into their ions, right?
They disperse into their ions. So we get our ions formed. So this guy is Mg. What is the charge on Mg?
Positive.
Is it just positive?
2 positive.
2 positive. And then sulfate, what is the charge on sulfate?
-3
Is it -3?
or 2.
Okay,
-2.
guys are rusty there.
Yeah, I need to go over it.
Okay, so -2, right? Okay, now compare that to sodium salt.
And ACL.
Okay, and then what happens when we put salt into solution, into water?
Na plus and Cl negative.
Okay, now these are interacting with the water molecules. Who's going to have a stronger hold on the water molecules? Sodium or magnesium?
Say magnesium, right?
Why?
Mm. Just has a greater charge, maybe?
Because it has a greater charge. Because it has a greater charge, it's going to sit there and be more attractive towards that water molecule. So it's going to be able to hold more of those water molecules together compared to what you're going to get for that sodium. Does that make sense?
Yeah.
Because it's based upon, even though those are partial charges, you're going to have a grasp on more water molecules. You're able to hold more of those water molecules together, and in addition to the water molecules interacting with each other, you have them interacting with that particular ion. So that charge is also going to have an effect. Okay. So when we think about things, right, we know that those charges are going to have effects on things. Also, we know that the fact that when we increase the molar mass, let's say in the case of the halogens, as we go down the periodic table, the molar mass increases. And as that molar mass increases, the melting point increases. Well, that's also going to be a factor of the fact that the radius are also increasing. That means that those electrons that the bigger molecules are going to have electrons that are farther away from the nucleus, right? And so those electrons are going to be able to add more polarization to the molecule, causing them to stick together a little bit better. So the bigger you are, the more you're going to stick to things. Does that make sense?
Yeah.
Okay. Are you with me so far?
Yep.
Okay, so I have a question for you here. Okay, so now knowing kind of what you know, I want you to look at these molecules here. So these are all isomers. They're all pentane isomers. So we have neopentane, which looks like this, right? And this is the what is it? Space-filled model. And then this is isopentane, right? So, and then this is N-pentane. So these are three different isomers of pentane. Okay, so these are the boiling points. We have a 9.5 boiling point. We have a 27 degrees Celsius boiling point, and we have a 36 degrees Celsius boiling point, right? So why do you think these guys have different boiling points, even though they have the same chemical formula? What is the distinction between these guys?
Stronger bonds, maybe?
They're all covalent bonds. So how are you going to
Well, it's true.
all single bonded?
Yeah.
Are they distributed differently?
So what do you mean by distributed differently?
Because the structures look different from each other.
Okay, so the structures look different from each other. So that's a valid point. So we know that they're isomers of each other. And we also notice how those structures are made, right? For instance, for neopentane, it actually has carbon in the center, right? So in terms of contacts, you have this be able to contact something, this is able to contact something, this is able to contact something, this is able to contact, right? But that center carbon isn't going to be able to contact anything because you have all the other carbons kind of protecting it, kind of showing here, right? So that one has less contact, right? Where the isopentane has one of the carbons kind of surround it, but you still have two areas, you have contact areas. So it has a little more contact area than the neo, right? And then the one that's linear, all of the carbons have the ability to contact things. So in that context, those carbons there are going to be able to sit there and interact better. Does that make sense? So less area of contact, more area of contact. It's kind of like Velcro, right? Have you guys played with Velcro before?
Yep.
So if I have a little piece of Velcro, is it going to be really hard for me to sit there and take it apart?
No.
Yeah, because it's smaller. It's got a smaller surface area.
So are you telling me it's going to be harder for me to take it apart, or is it going to be easier for me to take it apart?
Harder because it's smaller.
Are you sure? Is it going to take more energy for me to sit there? Because Velcro is basically just two things that are kind of sticking together. If it's small, is it going to take me a lot of energy to sit there and take it apart? So we'll put it like this. If
You're talking about, okay, so you're talking about energy, not the actual act, because I'm sitting there thinking I'm going to fiddle with a small piece of Velcro. It's going to be hard.
Well, that's the act itself. Even with that, let's say I have really good fingertips and I can actually.
Okay, so that way, no, it'll be easy.
Okay, so it'll be easy. So if I stuck a picture on the wall, a little piece of Velcro, like little piece of Velcro, would I expect that picture, let's say the picture weighs about 50 pounds, right? Would I expect that picture to fall, or would I expect that picture to continue hanging? So if I just use a little bit of piece of Velcros, like I use a little bit on the wall and a little bit on my picture, would I expect it to sit there and paint? Okay, so this is what we're gonna do. I want you to get your favorite picture that weighs 50 pounds. And I'm gonna give you guys each a little bit of piece of Velcro, stick on the wall and stick on your picture.
Well, that's because I'm thinking like Command, because those things are really like they stand by their product, but I'd still put more.
Uh-huh.
So I'm gonna say no, it's not gonna hold it.
Okay, it's not gonna hold it as well as you would get something that has a bigger strip, right? A bigger strip has more contact area, right? The more contact area, the stronger it's gonna be. Does that make sense?
Yeah.
So it takes more energy to sit there and break something that has long, that's really long and sticky together compared to something that's really small and sticky together. Does that make sense?
Yeah, I
Yeah.
think so.
Okay. So I want you guys to use those skills there. Your brain now. Now that your brain is working and everything like that, I'm going to put you guys in two groups. Maybe. And then I want you to look at this next question and think about it. Two groups. And come up with your rationale. Okay. Order the following compounds of group 14 elements and oxygen from lowest to highest boiling point. CH4, CiH4, GeH4, SnH4. Explain your reason. Okay, so I want you guys to go in a room, discuss it with each other, and come up with your answer. Okay, I'll give you guys, we'll say, it'll take you 10 minutes.
Sure.
Okay. Rooms are open. You're back.
Yep.
Excellent.
Yep.
You're back early too.
We try.
Good, good. So you guys have a good answer.
We hope.
Good, good. Okay, everybody's back. Okay. Okay, let's see those answers. What do you guys think? Group 1, Cassie, Kayla, Selena.
We had kind of gone with the radius, since all their structures were similar and they had 4 valence, so we just went with the radius. Kind of like what you were saying with the Velcro, like the bigger
Okay.
you are, the stronger you are.
Okay, so let's put it in order then.
So let me pull up the thing. It was the CH4, I think. Hold on. I gotta get the folder. Yeah, CH4, SiH4, GE4, or H4.
Write it on the board, please. On the
Oh,
whiteboard. Sorry. Okay, and group 2, what did you guys think? You agree with them?
Yeah, it was already in order.
Okay. Okay, and so, and you guys are basing it solely on the size of the center atom, since that's the only thing that's changing, the radius.
So our approach was that we just added up the molecular weight and
Okay.
put it from lowest to highest.
Okay,
I don't know if that's going to work in every situation.
so in this case, since they're all in the same group, it's going to work out, right? But let's say they weren't in the same group and they just happen to have the same molecular weight. Would we expect those guys to have the same boiling point?
No,
Why not?
because they're not how do I explain this? Because they might have the same molecular weight added up, but that doesn't mean that they're stronger than one another.
Okay. So we showed an example of that earlier, right? Where we have the isomers of pentane, right? So we have the neopentane, we have the isopentane, we have the N-pentane. And we know that all of those they all have the same chemical formula, which is C5H12. Okay, so here they all have the same chemical formula, but they all had 3 different boiling temperatures, right? The one that had the most contact, the neopentane, had the highest boiling temperature. The one that had the least contact had the lowest boiling temperature, right? So that's an example of why we can't just say, okay, molar mass, if we looked at the molar mass, isn't the molar mass of all these going to be exactly the same?
Yeah.
So in a sense, if we sit there and said the one that has the most contact, well, we assume that the one that has the biggest radius is going to have more contact because there's more area to contact, right? Okay. So does that make sense? You guys are feeling it or not?
Yeah, I'm feeling it.
Okay, good. Okay, let's get back to the slides. Okay. So if we look at real life, right? There is there's the gecko, right? So the gecko's foot. So if we actually take a look at the gecko's foot, it has septia, which are just little tiny hairs, right? And these little tiny hairs, they kind of branch off and have these little triangular tips like this, called spatula. So those guys allow more sticky, and their stickiness, right? Gecko could kind of turn on its stickiness, more or less. So it increases that stickiness. So lizards are able to sit there and crawl up walls, kind of like Spider-Man because of that, right? Have you guys seen a lizard crawl up a wall? No? Yeah.
Yeah.
Okay. So that is a really live example of that adhesiveness, right? Of the fact that the geckos are able to sit there and stick to the wall. Okay, because of those forces. Okay. Okay, so we've talked about dipole attraction, right? So dipole attractions. So the fact that things are charged are also going to play a part in that. And that's going to help us in terms of that orientation. Okay, so when we compare molecules that are similar in molar mass, the one that have the stronger forces are going to have an increase in boiling point, right? So something that is more polar is going to be more, is going to take more to boil than something that is less polar. Make sense?
Yes.
Okay. We've talked about hydrogen bonds, right? So water is the example of hydrogen bonds. Now, this here is kind of important here because we know that hydrogen bonds are like, again, they're dipole-dipole, but they're stronger because the electronegativity that's involved, right? And so since there's such a large difference in electronegativity between hydrogen and nitrogen, oxygen, and fluorine, then the strength of of the hydrogen bond is greater than that which you see with a normal dipole-dipole attraction. Does that make sense? So the strength of electronegativity are also going to be a factor. That's what I'm saying. So are you with me so far?
Yeah.
Okay. Okay. Ooh, got hit myself. Okay. So in the case of, let's say, water, right? We know that water is H2O. So if we substitute water with H, hydrogen disulfide, hydrogen dihydrogen selenide, dihydrogen telluride. And dihydrogen polonide. Okay, so actually we don't have to do that. We'll just let's do these four right here. More about that guy. Okay, so these four, if you guys can do me a favor and put them in order of boiling points. And then we'll do HF, HCl. We'll do HBr and HI. And let's do ammonia. No yawning. Are you calling me boring? Is that what you're saying?
Coughing, sorry. You caught me right as I was muting, so it sounded like a yawn.
Okay. Okay, so put these guys in order of boiling points. Okay. You guys got them? I'm gonna put you in groups again.
Oh, hold on.
There.
Oh. Okay.
Okay, gonna open up the rooms. You guys have 10 minutes. Ready?
Yep.
Did we lose somebody? Oh, that's only half you guys. You guys are just on top of it. You're a little ahead of the game there. Okay. Let's see. So what did you guys think?
I mean, we thought the same thing as the last questions you gave us. It's based on radius, but
Okay. Group, so let me see we'll put your answers up on the whiteboard again. Let's see. Okay, so group one, you put your guesses over here. Group one. And group two, you put your your hypotheses over here. I shouldn't say guesses. Hypotheses.
Which one was group 1 and group 2? Sorry.
I'm sorry. Group 1 would be Matt, Sadie, and Selena, and group 2 would be Abby, Cassie, and Kayla.
Okay. Cassie, you might have to write it down because I didn't keep the picture.
Okay, I was just pulling it up right now.
Okay.
Group 1.
Do you want ammonia and all that one too, or are we doing that
Yeah.
one together?
Yep, I want that one as well too. Group 1, are you there? Okay. It's like, what's happening?
Wait, Dr. Henry, we had to order like all of the molecules you had on the whiteboard, right? Not just
Yep.
like the
Oh,
first
no.
four.
Just the groups themselves.
Oh,
Yeah,
so
so
oh, okay.
and then we can talk about the cross groups afterwards. Selena, always going for the harder question.
I just want to make sure. Dr. Henry,
Yep.
we were kind of stumped on how to order it because we didn't know if it was like either the radius or the electronegativity because they
Okay.
can flip either way. So I have no idea.
Okay. So it's a hypothesis and we'll talk about it. But I wanted you guys to think about all the possibilities. So group 1, you're saying that it's increasing in terms of in this direction. Is that what you're saying? I mean, group 2.
Yes.
Okay. Okay.
Right, Kayla and Abby?
Yeah,
Okay.
Mm-hmm.
that's what we agreed on.
So no guesses? You guys are not gonna give me the guesses for the other ones? Group one?
To be honest, I really just don't know. I couldn't even guess.
Selena, you're not gonna put up a hypothesis?
I can put something, but
Oh,
I'm not
put
gonna
something.
guarantee that it's right.
That's all right. This is a learning experience, but I want to see what you guys are thinking. What do you think?
Okay.
So is this in terms of increasing?
Yeah.
Okay.
I tried my best.
Hey, that's what we can do. Okay. Okay, so let's talk about this, right? Let's see. So everybody has a, I'm gonna save your pictures here. My benefit. Okay, so we know that we talked about the hydrogen bonds. So who's going to be forming hydrogen bonds?
Anybody with hydrogen, fluorine, nitrogen, and oxygen.
Okay, so let's circle the ones that are going to be forming hydrogen bonds. Okay, so we know that these guys have stronger interactions, right? So if we actually start looking at the actual melting points of these molecules, where is it? There we go. So if we went by the trends, like you guys were saying earlier, group one, I'm sorry, group two. Group two was sitting there suggesting that it would be hydrogen, water, dihydrogen sulfide, dihydrogen selenide, dihydrogen telluride, right? So this is what you would expect the trends to be if you weren't taking into consideration hydrogen bonding. Hydrogen bonding, because the strength of it is so strong compared to dipole-dipole, the actual boiling temperature of water is 100 degrees, right? The boiling temperature of hydrogen fluoride is 19 degrees, 19.5 degrees. The actual temperature of ammonia, boiling temperature of ammonia is 33.34 degrees Celsius. Okay, and so just the addition of those strongly electronegative entities causes a huge crease in terms of the boiling point. Does that make sense?
Yeah.
Yeah.
Okay. So that kind of gives you an idea of that connectiveness that's going on there, right? Because I mean, you would expect it to be, water to be somewhere between 50 and 100 degrees, based upon the trends, but that's not the case. Okay. So we have to take these factors into consideration when we're doing our calculations. That's the bottom line. So you need to take into consideration whether it's going to be a hydrogen bond. That's the reason why hydrogen bonds play a huge role, and that's why they have their own little special case. That because of biologists. Okay, because when we talk about DNA, what's holding the two DNA strands together?
Some organic compound.
No.
Oh,
Hydrogen
hydrogen.
bonds. Hydrogen bonds, right? So
Well, it was carbon or hydrogen, one of the two.
Okay, so we know that DNA molecules are going to be, if you guys took a bio course in the last couple of years, right? So you guys know that DNA molecules are held together. So it's a double helix. So those two strands are held together solely by hydrogen bond. Okay, so in that case, you can actually see the hydrogen bonds forming between the oxygen on the thymine here, and then on the nitrogen, and the hydrogens on the adenine. Okay, so then you're able to sit there and form that hydrogen bond between that oxygen and that hydrogen on the adenine. So that's the reason why A bonds to T, right? It has 2 points of hydrogen bonding, and then C bonds to G because you have 3 points of hydrogen bond. Okay. Are you with me?
Yeah.
Okay, so let's talk about liquid properties. So in the case of liquid properties, these intermolecular forces are also going to be playing a huge part in that. We already talked about water, right? The water molecule. So when we sit there and think about these forces, we have forces that are going to be cohesive. Cohesive meaning that their molecules are interacting with identical molecules. So that's the intermolecular forces between identical molecules. And we have what we call adhesive forces, meaning that we have forces of different molecules. Okay, so if we're talking about just water, molecules interacting with water, then that would be cohesive. If we're talking about water interacting with a salt molecule, or that would be adhesive. Does that make sense?
Yeah.
Okay, so if I'm looking at the meniscus, the formation of meniscus with water. So is that adhesive? Is it cohesive? Is it both? And if it is both, explain to me how.
Which was it? H2O and what?
H2O in a tube, the meniscus forming of a tube, like a test tube.
Adhesive.
Oh, so it's nothing. Yeah, it'd be adhesive, right? Because of the oxygen and the forces in between the two.
Would it be adhesive or would it be cohesive?
Well, the solution is cohesive, but isn't the water interacting with the gravity or the oxygen atmosphere's oxygen? That's why you
Okay.
get the.
So do you get the meniscus because of the water interacting with the air, or are you getting the meniscus because the water interacting with the tube?
I don't know. Kayla, you want to take it away? I can't rationalize anymore.
Yeah, I'm in the same boat.
It's there, but
This is so complicated. I'm about to kill myself.
it's not even
God.
complicated. But it's just like I know we've talked about it and we've gone over this, but then it's like my hamster's not waking up right now, and it's like
Okay.
trying to add everything else. Because the solution is cohesive, because it's only water. It's
Okay.
only
So
water.
so the solution is all cohesive. Okay. So we established that. So what is forming that meniscus though?
The friction, or I don't know, what
Okay. And what is friction?
a force. Dang it.
Obviously, it's a force, right?
It's the
So
forces.
again, it's an intermolecular force. So it's a friction between what? Water and what?
Whatever the tube is.
Whatever the tube is. So if the tube is plastic, so it is those it would be in that case adhesive forces between the water molecules and the molecules of the tubes. So if we're working with polyethylene tubes, this is a polyethylene tube, then it is polyethylene, right? So you're having adhesive forces between polyethylene and water in that situation. That's forming the meniscus. Okay. So we talk about surface tension, right? Surface tension is just the force of attraction between the liquid and the forces of attraction of whatever surface we're talking about, right? Or in that case, are with each other, right? Between the liquid molecules.
So this is like the buoyancy factor, right?
Yeah, and we're getting there. Yeah.
Physics is coming back. All right, I'm with you.
Okay.
I know you hate that term because we're in chemistry, but
No, that's all right. No, physics and chemistry, they're siblings, right? Although chemistry more
you
important.
came first.
Yeah, that's right. So then we have capillary action, right? So when things are being sucked up in a tube, have you guys had to draw blood and they prick your hand and they take a capillary tube and suck up the blood?
I do it all the time.
Yep.
Okay. So under those circumstances, how is that blood being sucked up?
A vacuum force.
Is it a vacuum force?
No, it's the force between the capillary beds or the vein versus the tube that you're using.
Okay. So again, it's also those interactive forces between the liquid and the tube that we're actually using. So that allows it to go up. If we spill wine, right? So what
That's a
happens-
bad day. Why would you talk about that?
Spilling wine, oh gosh. Actually, I took a bottle the other day, right? We use a paper towel. Why do we use a paper towel to sit there and do anything? What does it do?
Soaks it up.
It soaks it up, right? How? Why is it, I can stick a paper towel just slightly above it and just hold that paper towel and the wine will actually start moving up that. Why does it do that?
Because you're a magician. Because of the forces.
Because of those forces, okay? So the forces are going to play a huge role in that. And they also play a huge role in the properties of liquids, right? You guys know about viscosity. So viscosity is just basically the measurement of the resistance of flow. And then that's going to be a result of those forces as well too. Okay, so if we look at honey, how many of you guys eat honey? I love honey.
Yeah. Not excessively, but
Not a fan, if I'm being honest.
yeah.
So
I use
good.
it when I'm not feeling good type of thing, but I'm not like, ooh, let's put it on everything.
Okay, so how many of you guys eat motor oil?
All the time, of course.
Delicious, right? So if we look at honey and motor oil, right? Both of those guys are pretty viscous. Honey is much more viscous than motor oil. You sit there and you try to wait for honey to pour out, it takes forever, right? Because it's very, very viscous, right? So that viscosity is a result of those molecular, so the intermolecular reactions, right? The IMFs, okay? So our viscosity is going to be a direct result of IMFs. Mercury is very viscous because of of the IMF that's involved in there. Okay. Makes sense? Yes, no, maybe?
So they would be stronger with like honey and motor oil, and
That
they'd
is
be
correct.
weaker in like something that's less viscous.
That's right. So like
Okay.
gasoline.
Okay.
Oh, the slower it is, the higher viscosity.
The force, yeah.
Mm.
Yeah. And so the stronger molecular forces that you have involved, the intermolecular forces that you have involved, the stronger the viscosity is going to be. So in the case of honey, you'd assume that there's a lot of strong IMFs there, right? Because it's so viscous, right? We know that water is pretty viscous. It's, well, relatively viscous compared to everything else. And that has a hydrogen bond. So we know that honey must have quite a few hydrogen bonds going on, right?
So does the formula vary, because it says it's variable? Is that just based on like additives or where it's coming from, or like what they're actually, like the pollination factor?
Well, because you're looking at a couple of things in terms of honey, right? So a lot of it is going to be sucrose, right? So you
Okay.
have the sucrose molecules, but honey also has other factors that are in it, right?
Okay.
So if we put, so it has also longer chains of sugar molecules in there. It also
Okay.
has some protein and stuff in there. And so all of those things, and that's why the formula varies. So it's a mixture.
okay.
And then the same thing with motor oil. Motor oil, although a lot of it is going to be oils, but it's going to be varying chains of oils,
Okay.
where everything else there is kind of pure. Okay, so adhesive versus cohesive. So cohesive forces are just those forces, meaning, like cooperate and stuff like that. So those are going to be identical. Adhesive means that you're going to have things that are going to be different molecules interacting. Okay, and these are going to play a factor on terms of surface tension, because let's take a look at this bug on water, right? So we have the bug's leg. So it's going to have adhesive forces acting at this point. And then we have cohesive forces acting underneath in terms of the water. Okay, so that surface tension is going to be primarily that adhesive force, because it's the bug on the water. Does that make sense?
Yeah.
Okay, so here we have like a water droplet sitting on a spider web, right? So the thing that allows it to nucleate on a spider web is going to be that adhesive force. And then, but the large, or the how big that water molecule gets is going to be a result of that cohesive force. Okay, and so, and here we have mercury. So mercury forms a meniscus that looks like this. Where water forms a meniscus that looks like this, right? So in other words, your cohesive forces are going to be greater than your adhesive forces, and so your meniscus is inverted. Does that make sense?
So when you have the cohesive forces that are higher, you'll have the inversion.
Yeah.
Okay.
Okay, and we talked about the wine spilling. Okay, and so we could sit there and utilize certain aspects. So in this case, we can actually utilize so we can use capillary tubes, and we can kind of estimate how far up a capillary tube water is going to go based upon this equation here. So, and in this equation, we're taking into consideration the properties of the liquid. So if we're talking about water, right? So we know that rho represents the density, R is going to represent the diameter of that tube, the inner diameter of the tube. G is going to represent the gravitational pull, which is 9.8 meters per second. And then the radius, or I said radius of tube, H is going to be the height. That tells us the height that it goes up. And ST represents the surface tension. Okay, in your book, they use T, but I didn't want to use T because I always associate T with temperature. I didn't want you guys to make that mistake. Okay, so this is equation here. Oops. So if we have a at 25 degrees, how high would water rise in a glass capillary tube with a inner diameter of 0.25 millimeters? And for water, the surface tension is 71.99 millinewtons per meter. And the density is 1.0 grams per cubic centimeter. So we know that 1 Newton is going to be equal to 1 kilogram per meter second squared. Okay, so if we take our equation, what are you guys going to get? And theta basically represents the angle that your capillary is at. So in this case, your angle is going to be at 0 degrees. So then theta is going to be, so theta equals 0 degrees. So then cosine of theta, of 0 is going to be equal to 1. That's over. Okay. So what do we need to do?
Plug in all the numbers. So surface tension 71.99.
Okay, but the units are
Mm.
Newton meters. Millimeters.
Oh,
Yeah, so I was gonna say you have to convert all, make
Yeah.
sure they're all the same.
Okay. Okay, so let's change this into our standard units because we know we want this guy is in grams per cubic centimeters. So if this guy is in Newton meters, 71.99 Newton meters, or millinewton meters. We know that cosine of 1, so times 1, so we'll just leave that alone. And then we have millimeters. And we have the density, which is in grams per cubic centimeters. And then we have the gravitational pull, which is 9.8 meters per second. Okay, so we have to change, we get everything in the same units, right? So So if we change Newton meters into just newtons, use this conversion factor, we'd end up with just kilograms per second squared. So 2 times. We change these guys into meters, 2.5 times 10 to the minus, oops, sorry. If it's diameter, so we have to divide this by 2, sorry. So it's 1.25, because that would give me my radius. Oops. And if we change grams into kilograms and cubic centimeters into cubic meters, that would just be 1,000. It's 9.8. Meters per second. Sorry, I ran out of room. So then those meters are going to cancel out. kg is going to cancel out. And seconds. Oops, that should be seconds squared. So then our height is going to be 0.12 meters. Okay.
Dr.
Question.
New I got 0.112.
0.112. But if we
Yeah.
look at fig,
Oh, okay. Never mind. Gotcha.
okay. Questions, concerns, Cash?
Just crying over here.
Nothing to cry about. This is the easy part. Just remembering forces and trends. Okay.
Yeah.
So we're going to stop here. We'll pick it back up on Tuesday, on Monday, Tuesday,
Monday.
Monday. Okay. Monday.
Okay.
Okay.
Alrighty. Bye, everybody.
Bye-bye.
Bye.
Right.